Okay, so when you picture the solar system, we always had this sort of neat layout. Jupiter and Saturn, the gas giants, huge.
Right, the big ones.
And then further out, you've got Uranus and Neptune. We always called them the ice giants. The idea being they're mostly made of frozen stuff, water, methane, ammonia, kind of the twins of the cold outer edge.
Exactly. And that label ice giant, I mean, it's been in every textbook for decades, right? But it's actually facing a huge challenge now, a really fundamental one.
I mean, like, it might just be wrong?
Well, yeah. Many scientists are starting to think that label isn't just unsupported by the evidence we do have. It might be, well, yeah, basically wrong.
Okay, so that's what we're diving into today. We're looking at some really recent scientific reports, a lot of new computer modeling that casts serious doubt on this whole ice giant idea for the solar system's last big unexplored places.
Yeah, the big question we want to unpack is, are they really ice giants? Or could they be hiding interiors that are actually, mostly rock? Basically rocky giants.
Rocky giants. That sounds completely different.
It is. And the core of the problem, the reason this is so up in the air, is the data we have. Or rather, the data we don't have.
Ah, right. Almost everything we know, fundamentally their mass size, how that mass is spread out, it all comes from one source.
One single source. The Voyager 2 flybys. Incredible missions, but...
Yeah, Uranus in 86, Neptune in 89. Quick snapshots, really.
Super brief. So we're working with data that's nearly 40 years old now. It was collected with, 1970s technology?
And we're trying to answer these super complex 21st century questions about what's deep inside them using, that old data.
It's a massive constraint. And that constraint, that lack of sharp modern data, leads straight to this fascinating problem called compositional degeneracy.
Okay, compositional degeneracy. Sounds technical, but I guess it's key here.
It's absolutely central. It sounds like jargon, maybe, but think of it like this. Imagine you have a cake, a really complex one, and you need to figure out the exact recipe, how much flour, sugar, eggs, whatever, but you're only allowed to know its total weight and its overall size, like its volume.
Right. You could swap ingredients, couldn't you? Like use less flour, but more butter, maybe, and still end up with the same weight and size.
Precisely. You could have wildly different recipes that end up looking the same from the outside based on just those two numbers. That's compositional degeneracy.
So that's happening with Uranus and Neptune. The gravity and size data we have from Voyager isn't enough to tell the difference between different interior recipes.
Exactly. Mathematically, you can build models of the planet's interiors that match the known gravity and size, but have totally different amounts of rock and ice inside. The current data just can't distinguish.
Okay, let's talk recipes then. The classic one, the ice giant recipe.
That's the textbook model. A relatively small, rocky core, then this huge, deep mantle made of highly pressurized ices, mostly water, ammonia, methane, and then a thick hydrogen and helium atmosphere on top.
But the challenger, the rocky giant idea, where's that coming from?
It's coming from modern computer simulations. What they do is kind of start fresh without assuming the old model. They run tons of simulations with different starting mixes, and they find solutions that match the Voyager data but look nothing like the traditional view.
Solutions where rock makes up a much bigger chunk.
Potentially huge chunk. Let's look at the numbers coming out of these recent models. They're kind of mind-blowing. For Uranus, they look at this thing called the rock-to-water mass ratio, or RW. The models show it could be anywhere from 0.04, so very little rock compared to water, all the way up to 3.92.
Whoa, hang on. Nearly 4 times as much rock mass as water ice mass.
Exactly. That's a fundamentally different planet. It means maybe up to 75% of all the heavy elements inside Uranus could actually be rock and metal, not ice.
And Neptune. Similar story.
Similar degeneracy, yeah. The RW range for Neptune goes up to about 1.78, so maybe 64% of its heavy stuff could be rock.
So if the data can't rule out these rock-heavy models, the whole ice giant name just doesn't hold up scientifically.
It really doesn't, because it makes a specific claim about composition that we simply can't verify, and might even be the opposite of reality.
Okay, but wait. If they formed mostly from rock, how did they end up with atmospheres rich in things like methane? Didn't they need to grab lots of icy comets and planetesimals? That's always been the story.
That was the story. But this new idea actually fits better with some modern theories about how planets formed out there. These theories suggest the building blocks, the planetesimals in the outer solar system, might have been much richer in rocky refractory materials and organics than we used to think.
Okay, so they started rocky, but the methane, the volatiles.
This is where this really neat idea called the methane bridge comes in. It's a way to connect a rocky origin to the gassy planet we see now.
A methane bridge.
Yeah.
How does that work?
Basically, it suggests the methane wasn't there from the start accreted as ice. Instead, it formed inside the planet later. If those initial rocky building blocks were rich in carbon-based organic materials, which seems likely, then once the planet grew massive enough to pull in a thick hydrogen atmosphere, those organics deep inside would be under immense pressure and heat.
And they react. The carbon from the rocks reacts with the hydrogen from the atmosphere.
Precisely. Chemical reactions deep down would essentially create methane from the rock components and atmospheric hydrogen. So the planet synthesizes its own methane ice in situ after it forms.
Wow, so it looks volatile rich on the outside, but it didn't necessarily start that way. It cooked up its own ice from rock.
That's the idea. It completely changes the narrative. It's less about what it accreted and more about the chemistry happening deep inside now.
Okay, so that tackles the composition question, or at least shows why it's so uncertain.
Yeah.
But you mentioned other weird things about them, geophysical signatures.
Yeah, the composition puzzle is huge, but it's not the only mystery. Their magnetic fields are, well, chaotic. And their heat flow is also really strange, especially Uranus.
Right, magnetic fields. Earth's is pretty straightforward, right? Like a bar magnet, roughly aligned with the rotation axis. Jupiter and Saturn are similar, bigger versions.
Yeah, relatively neat dipolar fields generated deep in the core, Uranus and Neptune. Not even close.
What do theirs look like?
They're messy, really complex, lots of poles, not centered on the planet, and tilted way off the rotation axis. Uranus's field is tilted by almost 60 degrees. It's bizarre.
Okay, that is weird. What does that messiness tell us about what's going on inside?
It tells us the dynamo, the process generating the magnetic field, can't be happening deep down in a simple churning core like Earth's. For a field to be that complex and off-center, it almost has to be generated in a much shallower layer.
Shallower, so closer to the surface.
Relatively speaking, yes. It implies that whatever fluid is conducting electricity and moving around to create the field is confined to a thinner shell, not the whole deep interior.
And why would that happen? Why isn't the whole interior churning and generating the field?
The leading idea is compositional stratification, layers. Deep down, the materials have separated out based on density or chemistry, and these layers are stable. They don't mix easily.
Like oil and water not mixing, that analogy.
Exactly like that. It's called the immiscible layer dynamo theory. Simulation suggests that under the intense pressures inside, different materials, maybe rock settling below water-rich layers, form distinct, stable strata. This prevents planet-wide convection, that deep churning.
So the heavy stuff settles, forms a stable layer, and stops the deep mixing.
Which then forces the electrically conductive part, probably a water-rich layer, to generate the dynamo higher up in a shallower shell. And that shallow dynamo naturally produces a complex, tilted, off-center field like we see.
Okay, so the weird magnetic field is actually a clue, pointing towards these stable, unmixed layers deep inside. And you said this connects to their heat flow, especially Uranus.
It connects beautifully because you see a stark difference between the two planets. Neptune is internally active. It actually radiates more than twice the heat it gets from the sun.
Meaning it's got a hot interior, and that heat is getting out probably lots of churning and convection.
Right, vigorous internal dynamics. But Uranus is weirdly cold.
The cold heart.
Yeah, it barely radiates any heat from its interior at all. Its heat output is almost exactly what you'd expect just from absorbed sunlight. The internal heat flow is incredibly low.
So why the difference?
The stratification. That low heat flow from Uranus is seen as strong evidence that it does have those stable, compositionally distinct layers inside. These layers act like a blanket, trapping the planet's primordial heat deep down, preventing it from escaping.
Ah, so the same layers that mess up the magnetic field by confining the dynamo also trap the heat.
That seems to be the most plausible explanation. It links the magnetic mystery and the thermal mystery together through this idea of a stratified, layered interior. Neptune might be less stratified, or have some process that allows more heat to escape.
Okay, this is painting a really complex picture, but let's circle back to the rocky giant idea for a second. If these planets are mostly rock, and maybe less water-rich ice than we thought, where does the electrical conductivity needed for that dynamo come from? Isn't superpressurized water ice supposed to be the conductor?
That's the million-dollar question for the rocky giant model. If you reduce the amount of traditional ionic or superionic water ice, you need another source of conductivity. And this has pushed scientists into some really cutting-edge physics.
like lab experiments trying to recreate those conditions.
Exactly, and also computational modeling of materials under extreme pressure. We're talking hundreds of gigapascals pressures, way beyond anything on Earth.
And what are they finding? Can rock become conductive?
It seems like it might, but in a really weird way. The models predict that under these extreme conditions, the silicate rock, the silicon and oxygen compounds, doesn't just sit there. It chemically reacts with the hydrogen and water that is present.
Forming new kinds of materials, hybrid rock-water stuff.
Kind of, yeah. Things like Si2O5H2, IO2H2 novel compounds predicted to be stable down there. And here's the really wild part. These materials are predicted to enter a superionic phase.
Superionic rock. How does that work? Is it like superionic ice?
Similar concept, different material. Imagine the silicon and oxygen atoms form a solid, rigid lattice, like a crystal. But the hydrogen atoms, the protons incorporated into the structure, aren't locked in place. They can flow freely through the solid rock lattice, almost like a liquid.
So the rock frame stays solid, but the hydrogen protons move around, carrying charge, making it conductive.
That's the prediction. It provides a totally different way to get electrical conductivity deep inside a planet, even if it's rock-dominated. It means the dynamo might not need a massive water ice layer after all.
And it suggests the boundary between rock and whatever's above it isn't sharp, but maybe a fuzzy reactive zone.
Yeah, a chemically active region where these superionic silicate hydrates could exist and potentially generate the magnetic field. It's a major shift in thinking.
Are there any clues we can see from the outside, like in their atmospheres, that might hint at which model, rocky or icy, is closer to the truth?
There are potential tracers, yes. The chemistry of the deep atmosphere should reflect what's being mixed up from below. Carbon monoxide, CO, is a key one.
Okay, what does CO tell us?
Well, Neptune has a relatively high amount of CO detected in its troposphere. That suggests pretty vigorous mixing is dredging up oxygen-rich material, likely water, from deep down. That kind of fits the more traditional dynamic ice-rich picture better.
But Uranus, the cold, quiet one.
Uranus has basically no detectable CO in its troposphere. That's much easier to explain if its interior is stratified and rock-dominated. If there are stable layers, you wouldn't expect deep material, especially oxygen-rich stuff, to get mixed up high into the atmosphere, so no CO.
Interesting. So the atmospheric chemistry seems to differ in a way that matches the heat flow differences too.
It does seem consistent, yeah. Another really important tracer is the deuterium to hydrogen ratio, the DH ratio. That's thought to be a really strong fingerprint of where and how the planet formed and what materials it accreted. We need better measurements of that too.
Okay, so summing this up, we have this huge uncertainty about what Uranus and Neptune are made of compositional degeneracy. We have bizarre magnetic fields and heat flows suggesting stable internal layers. And now maybe even conductive rock is possible deep inside. The old ice giant label seems shaky at best.
Pretty much, yeah. The scientific consensus growing is that we just don't know for sure, and the old assumptions are probably too simple.
Which means we have to go back, don't we?
We absolutely have to go back. Resolving this identity crisis is now a top scientific priority. It's why the U.S. National Academies, in their decadal survey, strongly recommended a dedicated mission, the Uranus Orbiter and Probe, or UOP. It's the only way to break this deadlock.
A mission to Uranus. I mean, that sounds incredibly difficult. It's so far away.
It's a monster of an engineering challenge. You're talking about a mission launching, say, around 2031. It would take about 12 years just to get there. Arrival in the early 2040s. Neptune would be even longer, maybe 13 years travel time.
12 years. Wow. And power? Solar panels are useless out there.
Way too faint. It would have to rely on nuclear power sources, radioisotope thermoelectric generators, or RTGs, probably multiple enhanced ones.
And even with nuclear power, how much juice are we talking about when it finally gets there?
Not much. Late in the mission, the total power available might be equivalent to running, like, less than 5 standard 100-watt light bulbs. Everything has to be incredibly efficient.
And getting data back over that distance must be painfully slow.
Excruciatingly slow. Maybe about half a gigabit per day from Uranus. That's like 5 to 7 times slower than missions currently at Jupiter, like Europa Clipper. Every single bit of data will be incredibly precious.
So given all those challenges, what absolutely essential measurements does this UOP mission need to make to finally figure out if they're rocky giants or ice giants?
Okay, there are a few critical things. First, the orbiter needs to map the gravity field with way more precision than Voyager did. We need the higher order gravitational moments, specifically J6 and J8.
Voyager got J2 and J4, which tell you how flattened the planet is. Why are J6 and J8 the magic numbers?
Because J6 and J8 are much more sensitive to how mass is distributed radially, how density changes as you go deeper. Measuring them accurately lets you distinguish between a model with a big, dense core and one with density concentrated in a shallower mantle. It breaks the degeneracy.
Got it. That's the key measurement for the internal structure. What else?
Second, the probe. It needs to plunge deep into the atmosphere, down to at least 10 bars of pressure, ideally more, and it needs to directly measure the composition down there, get accurate numbers for things like CO, and especially that crucial DH ratio, the chemical fingerprints.
Okay, gravity and chemistry. Number 3.
Third, map the magnetic field in much finer detail. A sensitive magnetometer on the orbiter can precisely map the field's structure, which tells you about the depth and the state of that dynamo region we talked about. Is it shallow? How complex is it, really?
Makes sense. And fourth, I think you mentioned moons earlier.
Yeah, fourth is checking out the moons. Specifically, looking for signs of induced magnetic fields around moons like Uranus's Titania and Oberon or Neptune's Triton. An induced field would be strong evidence for subsurface oceans, which tells us more about the whole system's evolution and potential habitability.
Okay, so it's a tough mission, but with very clear goals. Why does figuring this out matter beyond just, understanding our own solar system better? You mentioned a galactic connection.
It matters hugely for understanding planets everywhere, because planets the size of Uranus and Neptune, sometimes called mini-Neptunes, or maybe bridging into super-Earths, seem to be the most common type of planet in the Milky Way galaxy based on exoplanet discoveries.
So statistically, these are the standard planets out there.
They appear to be, yeah, which makes Uranus and Neptune incredibly important. They are our only nearby examples, our local laboratories, our ground truth for this super common class of planet.
So when astronomers find an exoplanet of similar size and estimate its density, they're basically comparing it to Uranus and Neptune.
Exactly. They use models based on Uranus and Neptune to guess if that distant world is rocky or icy or gassy. But if our fundamental understanding of Uranus and Neptune is wrong, if they're actually rocky giants, then all those interpretations of exoplanet compositions might be wrong too. It could change our whole census of rock and ice across the galaxy.
So the ice giant label isn't just potentially wrong for Uranus and Neptune. It might be misleading us about thousands of other worlds.
That's the concern, which is why there's a push towards maybe a new classification that's more scientifically careful.
Like what?
Something like heavy element-rich giants or HERG.
HERG, heavy element-rich giants. I like it. It doesn't commit to what those heavy elements are, rock or ice. It just says they're dominated by stuff heavier than hydrogen and helium.
Precisely. It acknowledges the core truth. We know they're enriched in heavy elements compared to Jupiter and Saturn, but the exact raucous ratio inside is degenerate, uncertain, and likely complex, probably involving stratification.
So the bottom line is, the old label is out, the interior is a puzzle, and we absolutely need a new mission to get the data to solve it.
That sums it up perfectly, and it really drives home that even in our own cosmic backyard, the textbooks are still very much being written. We're still figuring out the basics for our nearest neighbors.
It's amazing. And thinking about Uranus again, with its super low heat flow, you said it's likely due to those internal layers trapping the heat.
Right. Strong evidence for stratification.
So if Uranus really did form from mostly rocky refractory stuff, and it has this internal structure that traps heat and maybe drives weird chemistry like superionic rock, it makes you wonder, doesn't it? What other completely unexpected chemical processes might be happening deep inside these HERGs, these heavy element-rich giants, the most common type of planet out there that we haven't even dreamed of yet, all hidden behind those mysterious layers.
That's the frontier. We might find whole new regimes of planetary chemistry waiting for us.